This is the second video looking at the integrated rate law. This one will be looking at first order reactions. A quick review: rate laws are a mathematical method to determine how fast a reaction occurs. The differential rate law looks at concentration versus rate, while the integrated rate law looks at concentration versus time. We will be looking at one reactant versus time. The data will be concentration and time. Graphing is usually helpful. You may need to mathematically manipulate and plot the data more than once, and you can determine if the reaction is zero, first, or second order with respect to a specific reactant. The definition of terms: A sub T is the concentration of reactant A at some point T. A sub O is the concentration of the reactant at the beginning of the experiment, time equals 0. K is the rate constant, and T is the time elapsed in whatever unit is given. The half-life of the reactant is the amount of time it takes for the concentration to decrease by 50%. The previous video looked at zero order. The rate of reaction is independent of the concentration of reactant A. The differential rate law is rate equals K. If you plot the concentration of A versus time, you get a straight line with a negative slope, and the absolute value of the slope is equal to K. The equation for the line is A sub T minus A sub O equals negative KT, and that will be on your formula sheet. If you plot the concentration of A versus T and do not get a straight line, then it is not zero order. And lastly, for a zero order reaction, the half-life is not constant. Now to look at first order. The rate of reaction is dependent upon the concentration of the reactant A. The differential rate law in respect to A would be rate equals K times the concentration of A. If you plot the natural log of A versus time, you'll get a straight line with a negative slope. The absolute value of the slope is equal to the rate constant. The equation for the line will be the natural log of A sub T minus the natural log of A sub 0 equals minus KT. If you plot the natural log of A versus T and you do not get a straight line, the reaction is not first order. The half-life of a first order reaction is constant, and because of that, and therefore a reaction with a constant half-life must be first order. Let's look at the decomposition of hydrogen peroxide. We run the reaction and get this data. If we were to graph it, it's pretty obvious this is not a straight line. If you just check the slopes, you see that from 0 to 6 seconds, you get negative 0.0833, and from 6 to 12 seconds, you don't get negative 0.0833. The slopes are very different, so even without graphing, you know it's not a straight line, so it can't be zero order. When that happens, you need another column, the natural log of the hydrogen peroxide concentration. You get those by plugging the numbers into your calculator and recording them, and for this data it looks like this. If you plot that data, it's a straight line. If you decide to go by the checking the slopes method, from 0 to 6 seconds you get negative 0.116. From 6 to 12 you get the same slope. So you can say here the rate constant is positive 0.116 per second. The slopes are the same, so this is linear, and the absolute value of the slope is the rate constant. Now if the half-life is constant, then the reaction must be first order. So sometimes you can look at the data and use this method. We can do that here. We see that from 0 to 6 seconds, we go from 1 molar to half a molar, that's half the concentration, and that takes 6 seconds. Go from 6 seconds to 12 seconds, and you go from 0.5 molar to 0.25 molar. 0.25 molar is half of 0.5. It once again took 6 seconds. We can even look at the next data point, and it's obvious that that is 6 seconds, and the same for the next data point. The half-life is consistent, so this must be a first-order reaction. That's how you use the data to determine if you have a zero or first-order reaction. Now, it turns out that the half-life is equal to 0.693 divided by the rate constant. So here, if we happen to plug the values in, we get a rate constant of 0.116 per second. And if you remember, the slope of the line was negative 0.116 per second. And since K is the absolute value of the slope, all methods give the same value for K. So for a imaginary reaction, if A sub 2 becomes 2A, this data is collected. The first question: what is the order of reaction in respect to A sub 2? Try to figure this out. Come back and I'll walk you through it. Go. The answer is first order. You start by saying, is it zero order? I would use the check slope method. I pick 0 to 10 seconds and get a slope of minus 0.044. I decide to check from 10 to 30 seconds and I get a slope of minus 0.0265. The slopes are very different, so this cannot be a straight line, so it cannot be a zero-order reaction. So now you say, is it first order? 3 ways to get the correct answer. But in any case, you're going to need the natural log of the concentration of A sub 2. So you plug those into the calculator to get these values. You can graph the data, and you note that that's definitely a straight line. So you would say, yes, this is first order. If you don't have graph paper handy, you can now use the check slope method. If you don't have graph paper handy, then you can use the check slope method. 0 to 10 seconds gives you this value. 30 to 40 seconds gives you essentially the same value. It's off by 1/10,000th, which is rounding error. So the slopes are the same. So this must be a straight line. So this is a first order reaction. You can also see if the data allows you to use the half-life method. If you look at the data, you see that at 0, 20, and 40 seconds, you go from 1.5 to 0.750 and 0.750 to 0.375 molar. So you can say that the half-life is consistent at 20 seconds. Only first-order reactions have a consistent half-life. So once again, yes, this is a first-order reaction. So now based on that, question number 2, what is the value of K? Stop, figure it out, come back, and we'll go through it. Go. And it turns out that there are 3 methods for getting this answer, but each answer should be 0.0347 seconds to the minus 1. Graphically, calculate the slope because the value of the rate constant is the absolute value of the slope. Pick any points. We went from 0 and 10 seconds. Run through the math, and you get K equals positive 0.0347 per second. You can use the equation. Plug in the values you know, then solve for K. End up positive 0.0347 per second. Since we know the half-life, we can also use the half-life equation. The half-life is 20 seconds. This is the half-life equation relating half-life and rate constant. Plug in the values, solve, and you come up with the same answer. Question number 3. What is the concentration of A sub 2 at time t equals 15 seconds? See if you can figure this out, then come back and we'll run through it. Go. And it turns out there are 2 ways to get this answer. If you have the graph go to 15 seconds on the x-axis and draw a straight line perpendicular to the x-axis until you hit the line of best fit. Make a 90-degree turn to the left, draw the line, and then read your answer off the graph. And I read this as negative 0.115. So I now know that the natural log of A sub 2 at 15 seconds is minus 0.115. To get the concentration of A sub 2 at 15 seconds, I raise e to the minus 0.115 power. When I do that, I get a concentration of A sub 2 of 0.891 molar. That's doing it graphically. You can use the equation. And remember that the rate constant figured out in the previous question is 0.0347 per second. Plug in all the values we know. Now solve for the missing value. So you get this, and now you have the natural log of A sub 2 being negative 0.1155. You're going to raise E by that amount to get the concentration of A sub 2. And so the concentration of A sub 2, doing it mathematically, is 0.891, essentially the same value we had before. So to review, the integrated rate law compares concentration with time. A sub t is concentration at time t. A sub o is concentration at time 0. T is time in whatever unit is given. K is the rate constant. And the half-life is how long it takes the concentration of a reactant to decrease by 50%. For a zero-order reaction, the graph of A versus time is a straight line. The integrated rate law is A sub t minus A sub 0 equals minus kt. K is equal to the absolute value of the slope, and T1/2 is not constant. It varies with concentration. For a first-order reaction, the graph of the concentration of A versus time is not a straight line, but the graph of the natural log of A versus time is a straight line. The integrated rate law is the natural log of the concentration of A sub t minus the natural log of the concentration of A sub 0 equals minus kt. K equals the negative value of the slope, or the absolute value of the slope, and the half-life is constant. It does not vary with concentration, and so if you have a constant half-life, it is a first-order reaction. The T1/2 equals 0.693 divided by K. So now we've covered zero and first order reactions. The next video will cover second order reactions.